Hello everyone, hope you're doing well. My name is Mahmoud Kiasser and welcome to this chapter of Advanced Algebra. So today we are going to talk about a very interesting topic, exponential and algebraic, some kind of functions, why they matter, how they're going to be connected to each other, and so on and so forth. If you can remember from the previous part, we actually talked a little bit about them, that especially when we were talking about the mirror, that y is equals to x was as a mirror, and we had e to the power of x and we have the ln of x. So right now we are going to talk about them in detail, having some kind of problems and solve them in order to completely understand what's going on. But just beforehand, we have to talk about a couple of laws related to both of them. So at this point, again, as I just told you, we are going to see that what would happen to these two important functions. And at the end of the day, we are trying to have a complete review of exponent and exponential function. We are going to understand the logarithmic as the perfect inverse. You have the tools to solve any kind of exponential or logarithmic equation and how we can apply them into the real world scenarios. Just before talking about the whole idea, let's touch a little bit points which is related to the laws of exponents. That actually we know about that, but it would be better to talk about it a little bit. We know about this law, it would be better to talk a little bit more to see that what's going on. So the very first thing that we have to know, the exponents and the expression is most of the time is just like this, a to the power of n. We saw it before, x to the power 2, x to the power 3, y to the power 2, and etc. So this guy simply means what? It simply means that we are actually multiplying one number, or we call it as a base, by itself n times. For instance, when I do have x to the power 2, actually I multiply x by itself 2 times. So we have two important parts. The first part is the base, and the second part, which shows that how many times we are going to do that, is called as exponents, or we just sometimes call it as a power. For instance, when we do have 2 to the power 3, actually we are multiplying 2 3 times by itself. We do have 8. When we do have 10 to the power 2, it just means that 10 by itself 2 times, which is 100. So we have to know a couple of laws related to exponents that we can use them. Because if you guys remember, especially from the previous part or from some kind of your high school, if you touch this subject, you will see that when we do have exponents and we're side by side, when we are talking about multiplication, division, and when we do have one of them in parentheses and another one on another side, we do have some laws. And most of the time, these laws would be about multiplication and division. Addition and subtraction, maybe we have something that's related to factoring, which is we don't care that much right now. The only thing that we care is about how we can multiply them if we do have two of those our terms as some kind of exponential expression. So let's see what's going on. So the very first thing is that when you face this kind of questions, that a to the power m times a to the power n, the only thing that you have to do, keep the base. Remember, we only can do that if we know the base is the same. We keep the base, and the only thing we have to do, just adding up those powers or exponents. For instance, I do have 2 times x to the power 3. You can some kind of write it down like this, and at the end you still have x to the power 5, or simply you can just write it down as x to the power of 2 plus 3, which is 5 itself. Another thing that we do have is the quotient rule, or we do have it as division rule. It means that when we do have something like this, a to the power m divided by a to the power n, the only thing that we have to do is subtract the n, or the one that is in denominator, from the numerator. And we do have it a to the power m subtracted by n, like this question itself. And we do have another rule of a power rule. What does that mean? At sometimes the number inside your base is itself was exponent functions, or some kind of was exponent term. How we can deal with that? If I do have something like this, the only thing that I have to do, I have to write down the base again, and instead of just adding or subtracting those powers, let's write it down as m times n. For instance, b to the power 3 times to the power 4 means that we are multiplying b to the power 3 4 times by itself. And again, if you use the first law that we had over here, add 4 times by itself, you still have b to the power of 12. So this is the first one. Another thing that we have to do is about some kind of exception scenarios that we call it. The very first one is about the zero exponent rule. What does that mean? Any non-zero number that raised to the power of 0 is always 1. It means that whatever number you have, it doesn't matter. It is negative, it is real, it is fraction. Whatever number that you have to the power of 0 is going to be 1 itself, until that number is not going to be the 0 itself. So that is another scenario. We don't talk about it. So it means that, for example, 7 to the power of 0 is 1 itself. On another hand, we do have negative exponent rule. What does that mean? The negative exponent rule signifies the reciprocal. It means that whenever you see a negative sign on your some kind of exponent, you have to follow the flip rule or the reciprocal rule. It means that you have to write down 1 on the top and write down the whole expression on the bottom without considering any negative sign itself. For instance, when you have 5 to the power negative 2, it actually was 5 divided. It was 1 divided by 5, but 5 to the power 2, 125. Maybe some of you would ask how, if you guys remember from the previous rule, I can write down any number as to the base to the power of 0, right? 5 to the power of 0 divided by 5 to the power 2. It would be 5 to the power of 0 subtracted by 2, 5 to the power negative 2, and as simple as that. So we just learned 2 important laws. Another thing that we have to know is about the rational exponents are the shorthand for roots. What does that mean? Imagine that they do have a fractional exponent, that it simply would be another way to write down the root itself. If you guys remember, the last part we touched a little bit about some root or cubic and what there's some kind of the simple root of 2, root of 3, and what would happen if you do have them inside the function itself. So this is going to be somehow another part related to that. So what does that mean? Let's see what's going on. The very first thing that we have to know is that a to the power of 1 over n is actually was root of a with n itself. It means that, for instance, if I do have a to the power of 1 over 2, actually I'm talking about root 2 of that one, which the root of 2. If I do have a to the power of 1 over 3, I'm talking about a with the root of 3. This is the rule. Another thing that we have to know some kind of is that we can consider this one that we can be combined to, and we have this one as another answer, which is not that important. We are going to use this factor. So again, 16 to the power of 1 over 2 is going to be root of 16 or root of 2 of 16, which is going to be 4 itself. Another thing that we do have, what would happen if our power is not just 1 over n or 1 over m? What would happen if we do have 2 of them at the same time? It's going to be m over n. So this is going to be general fractional exponent. It means that the numerator is the power, then denominator is the root. It means that my m is going to be the power and n is going to be root. It means that I can write down a to the power m divided by n as root n of a to the power of n or something like that. For instance, if I do have 27 to the power of 2 divided by 3, 3 is my root and 2 is my power. 27 to the power of 2 root 3, if you find that one, it would be some kind of 9 itself. So this guide is going to powerfully connect all of the exponent rules directly to their radicals itself, as we talked about it before. So let's talk about exponent function. What is the actual thing that is going to make them interesting? In other some kind of function that we saw, maybe linear function, about some kind of nonlinear function. By the way, nonlinear function means that you do have a function that it has anything rather than x to the power 1. It has x to the power 2, 3, so on and so forth. In y is equals mx plus b, everything was normal. It was just increasing or decreasing. In y is equals to x2 plus something, so we do have some kind of increasing another side, and everything was somehow normal, and it was based on the thing that we expect. By increasing the number, either I'm going to increase my final value or I'm going to decrease my input, and after that decreasing my input. But at the exponent function, the situation would be a little bit different. Why? Because at one point we see that my exponent is going to act slow. At one point, my exponent is going to act normal, like a linear one, and at some point, my exponent is going to increase drastically. So that's why this guy is so interesting. It means that at the beginning, everything is slow. By increasing the input number, everything is going to increase so fast. So let's see what's going on over here. Imagine that I do have this kind of form. Imagine that I do have this function itself is a times b to the power x. As you can see over here, unlike the last one, a nonlinear function before that was x to the power 2. But at this point, the x is the power itself. It means that by increasing the number x, we can see some kind of interesting changes in our function. So y is a times b to the power x. By considering the fact that b is bigger than 1, it is important, by the way, I will tell you why. So b bigger than 1 is the general form that we have. So this guy is going to start at the initial value of a. It means that it's going to have y-intercept at x is equals to 0. So as we all know, if we find f of 0, it's going to give us a number. It could be anything. And I do have the y-intercept with the y-axis itself. So for instance, if you put 0 at this point, and if I consider that b is bigger than 1, this part is going to be 1, and a is going to be y-interception. It means that I'm going to start from y is equals to a.
After that, the curve is going to increase slowly. What does that mean? It means that if you start from 0 to 0.1, 0.2, to maybe all the way to 1, you don't see that kind of changes. Your x actually is going to increase faster than your y. It's the characteristic of exponent function. So at this point, we do have very slow starts. It's just like the car. It needs to warm up a little bit. That's why it is slow. Then it's going to accelerate, not normally, but incredibly fast. What does that mean? It means that at this point, I do have a normal condition that it's somehow increasing linearly, but after some point, it's going to I'm going to have the rapid acceleration. What does that mean? Imagine that you have 2. At first point, 2 to the power 0, 1, it's going to nothing. And we do have 2 to 0.2 all the way to 2. I'm just increasing from this point to this point. It's going to only maybe around changes of 2. But at some point, I'm going to have 2 to the power 1, 2 to the power 2, 2, 3, 2, 4, and you just name it. I do have 2, I do have 4, I do have 8, and 16. Increase by 2, increase by 4, increase by 8, and so on and so forth. That's why it is increasing so fast, and that is going to make this guy interesting. So this common model, we can use it. It's about the population growth. That means that we start with something, and based on that, our population is growing based on the factor. Investment earning, we do have social media followers, and this kind of example could be a very good one to show you that what is happening over there.
Previously, we were talking about the function, exponential function, that f of x is equals a times b to the power of x. We talked about the condition that our b could be bigger than 1. And right now, we are going to see what would happen if b is going to be between 0 and 1. Something would change. So as you can see over here, again, I do have this function. It would be in this form. And my b, unlike the previous one, which was bigger than 1, right now it's between 0 and 1. So the key features over here is this. The curve is going to decrease rapidly first, then the rate of the decay is slower down. It's somehow completely vice versa of the previous guy. That guy was increasing so slow at the beginning, had around the linear section and increasing drastically. But right now, instead of just having everything like that, we do have it backward. It would decrease so fast, and we do have a linear section, and it would decrease slowly. So as you can see over here, imagine that I'm going to consider the y is equal, this x is equals to 0. Obviously, it's going to give me a y, because whatever number to the power of 0, as we know, is going to be 1, and y is equals to a times 1, it would be 0, and a, we do have this point. If we some kind of decrease, if we try to, by increasing the number of x, we are going to have the very fast decreasing at the whole function. We do have almost a linear section, and then we do have a very slow decreasing. So common models that we use for this one is the radioactive half-life, would be called about the car depreciation, and etc. So the examples that we can have is 100 times 0.8 to the power of x. You can just draw it by giving some numbers to your x value and find y itself. So let's talk about the logarithm. What is the logarithm? As we were just talking about it, logarithm is the inverse of an exponential. What was the inverse? If you guys remember, when we had f of x is equals x to the power 2, I told you this guy is going to be your y, right? F of negative x, or f of inverse of x, means that what is the actual function that it's going to be mirrored, while I do have y is equals to x as mirror on another side. And we learned that if we want to do that one, we have to some kind of change the position of y and x. So it would be x is equals to y2, and find again y based on x, so y with root of x, so f of negative x would be root x. We do have the same scenario over here. It means that whenever we do have the exponential function, we are looking for the mirrored guy. We are looking for the guy that is on the other side of the mirror, and that is something we call it as logarithm. So again, what exponents do I need to get this number? This is the main some kind of question. So let's talk about the definition again. We do have two statements below are logically equivalent. What does that mean? It means that b to the power of y, instead of just having the x itself right now, I do have the y, because that was the way we were trying to find our some kind of inverse. B to the power of y is equals to x, which was exponential form, and this guy means that log of x with some kind of base of a
is going to be y itself. So some kind of example that we can have, whenever we do have log of 8 with the base of 2 is equals to 3, why is that? Because actually this guy to the power 3 is going to be this guy. As you can see, something like this is happening. A to the power of y is equals to my x. So what is the big idea? The logarithmic is actually undo exponential. They're inverse functions. So let's talk about some kind of rules about the logarithm. As we just saw, it is the inverse of exponential function and it has a little bit of different rules. So logarithms have properties that is going to mirror the laws of exponential. Whatever law that you have about the exponential is going to be mirrored and allowing us to simplify the expression. First of all, let's talk about the product rule. It means that the log of a product is the sum of the logs. What does that mean? Imagine that I do have a condition, that I do have a log of m times n with the base of a. I can write it down as log of m with the base of a plus log of n with the base of a. So it means that at this point, m times n is actually going to be converted to something like this. For instance, I do have the log of 1000 with the base of 10. I can write it down as 10 times 100. Log of 10 with the base of 10 is going to be some kind of rule, or it's not that kind of hard thing to remember, but whenever you have some kind of the logarithmic number with the base of the same number, you are going to have 1. Whenever you have the log of 100 with the base of 10, you can write down 100 as 10 to the power of 2. So what is the number that if I write down it like this, for example, 10 to the power of y is going to be 10 to the power of 2, so your y is going to be 2 itself. I have 1, I do have 2, and my answer is 3. Right now, if I would like to write down the question again to see that my answer is right or not, I can say that log of 1000 with a base of 10 is going to be 3. So 10 to the power 3 is going to be 1000, so I'm right. Whenever you see some kind of a number with zeros, especially 1000, 10,000, 100, the 100,000, whatever, the only thing that you have to do, you have to find the power of 10 over here. You have to divide down the 1000 to some kind of the product of 10 after that, but you can consider that product as your final answer. For example, 1000 was 10 to the power 3, so 3 is going to be your final answer itself. What about the quotient rule? What would happen if I do have the division over here? The log of a quotient is the difference of the logs. It means that log of m divided by n with the base of a is going to be log of m with the base of a subtracted by log of n with the base of a. So at this point, when I do have m divided by n, I do have something like this, as simple as that. So let's talk about the power rule, the change of base formula. So what would happen if instead of just having a normal number, like 10,000, I don't know, 25, whatever, I do have something like this. It means that inside my logarithm, I do have a number that has a power. I do have exponential form inside my logarithm form, something like this. So that power rule would say an exponent on the argument of the log can be moved out front as a multiplier. What does that mean? It means that if I do have my k over here, I can say that k is safe enough to move around there. It means that I do have k times log of m with the base of a. Maybe some of you would say that, how is that possible? It's simple. You can prove it, right? So you do have k log of m with the base of a. You can say that log of a plus log of a, m with the base of a plus itself k times. So we know that log of number plus another log of number, if their bases are the same, can be written as log of m to the power of whatever that I need with the base of a. At this point, I'm adding this log of m with the base of a k times. So I can say that that was m to the power k, and as simple as that. So another thing that we have to know is the change of base formula. What does that mean? It means that this guy or this kind of formula lets you to evaluate any log on any calculator. You can convert the base or this kind of base. What does that mean? It means that if you do have something like this, it would be log of b with the base of a. You can write it down as log of b. By the way, whenever you don't see any base for your logarithm, it means that the base is 10. So since that is so common, they are going to get rid of that. Divided by log of a. Or ln of b and ln of a. What is ln? Ln is a very specific form of exponential is some kind of a function or logarithmic function when you have something inside your number, inside your log, and your base is going to be e or Euler. Euler is a specific number that is like 2.71 and actually continues, but instead of just writing it down like this, they're going to call it as ln. So we can do that as well. For instance, if I would like to find the log of 7 with the base of 2, at some calculator it would be a little bit challenging because most of basic calculators, the only thing that they have is just log and ln. And for advanced calculator, we do have log and be the base that we can consider. So what we can do on that time, we can divide it based on this rule or some kind of write it as one log or one ln on the top and another ln on the bottom, while I consider the base on the top is going to be, for example, 10 and bottom 10, but the numbers is going to be the number inside the log 1 and the base of the first number. So as you can see over here, the log of 7 with the base of 2 actually can be written as what? As the log of 7 divided by log of 2, or we can write it down as ln of 7 divided by ln of 2. Whatever number that you have is going to be your final answer itself. So a very important toolkit for solving the exponential equation. What does that mean? It means that at some point when you do have your exponential function, you need to some kind of solve an equation. So it means that something like the question that you can see, I do have 2 to the power 3x is equals to 2 to the power 9. At some point, the question would be so simple, but at another point, it would be a little bit challenging. Let's see both sides and see what we can do in order to solve this equation without having any sweat. So the very first one, it means that if the bases matches, we love this kind of question. What does that mean? It means that I do have an equation, and it would be like this. 2 to the power 3x is equals 2 to the power 9. So it is simple. I know 2 and 2 are equal. So the only thing that should be equal is the power itself. 3x is equals to 9. And after that, x is equals to 3. Simple as that. But the condition would be a little bit challenging that the base are going to be different. So at this point, again, we do have solution. So I have to take the log or natural log or ln. Natural log means that just the logarithm with a base of 10. ln means that the logarithm with a base of Euler of both sides. If you guys remember, this is what we did for solving some kind of equations. We add, subtract, multiply, or divide both sides by something in order to simplify the thing. Because the idea over here is that I do have x to the power. Like this situation that I do have x to the denominator, I would like to somehow get rid of that and move x to be on the ground, not on the top, not at the bottom, into the ground. So when I do have something like this, I have to use ln or I have to use the log, there's some kind of the log format. So this one allows you to use the power rule and bring the variable exponents down. I would like to bring this guy down because it's on the top. It would make the situation complicated. So what can I do? I can use ln from both sides. Actually, this is the time that you can say that I can cancel them out, but we are not talking about it actually, but this is something that you can do, or you can find the log. Let's just work with ln. So ln of 3 to the power x, as we know based on the power rule, I can move the x to another side, right? So I can write it down as x times ln of 3. ln of 20 is just a number, right? Whatever number is that. So I have to get rid of this ln 3. It means that I have to divide both sides by ln of 3, divide this guy by ln of 3, and then I do have something like that. That would be simple. Use a calculator and you can find your answer. It's as simple as that. So what would happen that if you're trying to solve some equations and we see some pitfalls, we see some problems that I saw in students, that at this point I'm going to talk about in order to help you to not get trapped inside. So the main strategy over here is that isolate a single logarithm term and convert the equation into the equivalent exponential form. What does that mean? You have the log of x minus 1 with the base of 3 equals to 2. So one thing that you know for sure is that this guy equals to the power of this guy, 3 to the power 2. This guy is 9 and x is equals to 10. Simple. But what would happen if we do have the combination? What would happen if we do have something like this? At this point, we are going to use our first rule. What was that? Whenever you have the two logs with the same base and they're adding with each other, it means that you can simplify it by this multiplication, right? And that would be simple, right? Because I do have the log with a base of 10. 10 to the power 1 is going to be equal to this one. I can get rid of log as fast. It means that x times x plus 3 is equals to 10, and you can find it. So critical warning is that all the time you have to check your solution, because the argument of algorithm, some kind of the logarithm, is that they should be positive. What does that mean? It means that whenever we're talking about the logarithmic function, we are talking about another thing. As you guys remember from previous slide, whenever I do have the log of a number with the base of something is equals to something else, I can convert it back to the exponential function. And the answer of exponential function all the time is going to be positive. It doesn't matter it's between 0 and 1 or it's bigger than 1. All the time is going to be positive. So when you have a log of a negative number, you're disobeying a law. That law would says that I do have an exponential function that its answer could be negative. It's completely undefined. So that's why whenever we solve this kind of equation, whatever x is, first of all, we have to have some kind of constraint domains for ourselves. If you guys remember from the radicals, we knew about that, right? So whenever you see that log of x plus 3, for instance, you know for sure that your x should be bigger than what? Your x should be bigger than 0 for the first one, and your x should be bigger than negative 3. So since you have both of this guy, you have to find a common range that would be acceptable for both of these logarithms. So if you find a common spot, your log should be bigger than 0. On that point, if you find an answer, if you use it over here, you don't have any negative number, you don't have any issue. So for this point, for instance, we see that I do have x is equals to 10 as my answer. So for example number 1, I'm going to use it checked. Everything is okay. And also the 9 is positive, so I don't have any solution and everything is going to be valid. So let's talk about the real world application and how actually we can use that. Imagine that we are talking about the exponential growth of money. Actually, this is very common formula for economics, for the whatever related to finance, and you can use something like this one. A is P, which is going to be your principal or initial amount, times 1 plus R divided by N. What is R? Is the annual interest rate. N is the number of times interest in some kind of compound per year, and T is the number of years itself. So this is a formula. You don't have to worry about it to memorize it. This is just a formula that shows how we can use the exponential function growth, right? So this formula is going to say us that the direct application of exponential growth modeling and anything with a fixed percentage growth per period. It means that at the beginning of the point, I do have my P as the initial value. By increasing the time, which is T, and since T is on the power, it is something like a to the power of x. Whatever that we do have over here is just this one, and x is exponential. And if you remember, since everything over here is positive and most of the time bigger than 1, I'm going to have this slow increase at the beginning, a linear section after that, and drastically increase at the end itself. So what would happen if you talk about the half-life and the population of models? So we do have a model like this that n0, whatever, some kind of we had at the beginning, times half of t to the power of h. So t over power of h, because at this point, my h is going to be in denominator, whatever is that, and also the fact that your base is something between 0 and 1, we do have something like this. Decreasing so fast, linear, slowly. On another hand, we do have the continuous growth of bacteria. So I do have some first numbers, after that e to the power of kt. E is just the Euler number, 2.71, whatever. After that, we just, it also has other numbers, but most of the time take care of the first two things, first two or three. And since the number is bigger than 1, so you do have the drastically growth itself. So the journey and some kind of your journey for the next part would be about this path. We talked about the exponential rule as some kind of, we had the exponential function, we had the log law, solving equation, and real world application. So try to think about other kind of functions that you can see in the real world scenarios. You can just Google it, you can just find some kind of functions and see that how actually they're going to grow. It's just like a curve or just like this kind of curve, and you can see actually you are surrounded by logarithmic functions and exponential function. Try to again
rewatch the video, try to look at all of the definition, all of the examples that I gave it to you, try to understand and digest all of the parts, pause it, think about it, find some kind of other examples for yourself, and if you have any problem, just put the comment. I can help you obviously with that, and if I couldn't, I probably make another video that has some kind of more example in it. Thank you very much for being here with me. Please don't forget to like, share, and comment. Have yourself a great day, night, whatever. See you.